Most of us spend our day surrounded by batteries, but have you ever wondered how a battery works? Well, if you haven't, then you're just going to have to fake your enthusiasm because we're going to learn about it right now. And we're going to look at batteries from a chemist's point of view. Because, look at the first sentence. Batteries are slow chemical reactions involving the transfer of electrons. That's with the E, with the negative sign here. That means electrons. Through an external path. The external path is this. Notice the arrow is showing the direction the electrons are traveling. It is a system, this is the big deal. It is a system for the direct conversion of chemical energy into electrical energy. So that's the energy of bonding, the potential energy in the molecules, and we're going to convert it into a useful electrical energy. One reaction spontaneously, when we're looking at the chemical reaction, we can break it down into two half reactions. And in one chemical reaction, she produces electrons, and another reaction consumes those same electrons. So they used to say it was akin to marriage, love and marriage. You can't have one without the other. Now that's kind of old-fashioned for sure, but it is a thought. Electrons flow from the so-called anode, and I do want you to know these terms, to the cathode. You'll notice electrons E and A. Electrons are produced at the anode, so I try to remember it that way, vowel to vowel. And they are consumed at the C for calories. No, but I just like to use mnemonic devices that are kind of silly, but they help me. So the positive cathode, the negative anode. Here's an example of two reactions. Okay. They're a little bit more complicated than we may be used to seeing, but what you are looking for, friends, is the production of those little electrons. Notice at the anode, the electrons are a product, and up here at the cathode, they are a reactant, and so they are consumed. The flow of electrons is the so-called electricity. The drive to push electrons through the external path is called the voltage. Okay. Chemical reactions involving the transfer of one or more electrons between reactants are called redox or oxidation reduction. We're not going to spend a lot of time with this, but just so you know, oxidation is rusting. For example, a nice metal like iron sitting here. Let me get my pen again. Yes, pen. I want a pen. We have iron right here, like a piece of gray iron. It meets up with oxygen gas and it rusts. That's Fe2O3. This is my rust. And we say that the iron is oxidized. He was neutral there, and he has a +3 charge in this ionic compound. So he has lost 3 electrons. The oxygen, she is neutral here too, but when she's in the ionic compound, remember this is an ionic compound, so they have a charge, the 2 cation and the anion, and the oxygen has a -2 charge. I've got 2 irons and 3 oxygens, and that works to make the overall species neutral. Okay, so what has happened is the electrons from iron have been transferred over to the oxygen, making the oxygen negative and leaving the iron positive. So let's write these down. Let's do another example. And we're going to do this in worksheets too, but it is a very important type of chemical reaction, so we're going to sit on it and spend some time with it. Okay, so this is the overall. I've got nickel ion, nickel 3+, going to reacting with cadmium Cd to produce nickel 2+ and cadmium 2+. Notice that she's gone from a +3 to a +2 or 2+. Remember, the positive sign is usually written after the number to indicate that that's an ionic charge. I should have done that up here as well. I'm sorry. So that would be 3 plus and 2 minus. Well, that's nice and clean, but you get the idea. All right, oxidation is the loss of electrons. And I love this little mnemonic device down here. Oil rig, oxidation involves losing electrons, and rig, reduction involves gaining electrons. Or Leo says GER, loss of electrons, oxidation, gain of electrons, reduction. Okay, so we have one guy losing electrons, and so this would be oxidation. And then we have somebody else gaining electrons. Notice if he gains electrons, he becomes less positive. In both cases, though, I have 2 electrons. That has to be the same in both of those half reactions. So when I add these guys up, they become the total over here overall. Let's do it again. Galvanic, it's the transfer of electrons. And let's talk about a general one where the cadmium's oxidized, nickel is reduced. I can write it as, again, 2 half reactions, an oxidation and a reduction. The overall, if I add these 2 up together, is this one. And it's kind of strange, but when we're talking batteries and these kind of redox reactions, we have no problem including simply the ions, not the ionic compounds, because the other guys are not really doing anything. So this is the bare bones of what's the reactions occurring. So up here in the oxidation, remember oxidation is loss of electrons. Hello, there they are. And reduction is gain of electrons. Okay. And if we notice that when we add these 2 up together, okay, the electrons cancel out. The overall cell reaction does not have any electrons in it. They must cancel. Okay. All right, so a battery is a self-contained electrochemical power cell. That means I'm making electrons out of the chemical reaction. And it includes one or more voltaic or galvanic cells, same thing. When the cells are connected in series, greater voltages can be achieved, like the one in a flashlight. So you put 2 1.5 volts together, and they just simply add up. Okay. However, this is what I want you to appreciate. This is kind of the new thing. You probably know that if you put them together like this in your flashlight or other household devices, you put in more than one AA or AAA, and that's very common. But this one I want you to appreciate. The voltage of the individual is due to the chemical system. What's the chemical reaction happening in this guy? And so if you look at all what's called alkaline batteries, so that's the kind of chemical system, from a AAA all the way to the big fat D, they're the same voltage. So I want you to know this. And the larger has more chemicals. It has more concentration of the chemicals of the reaction, so she lasts longer. So a D will last longer than a AAA, but the voltage, the push of electrons, is the same. A 9-volt alkaline battery, she'll have 6 1.5 volt batteries in series. So we do 6 times 1.5 equals 9 volts. She looks different because she's got both her cathode and anode pole at the one end. And if you want to have some fun, don't tell your mother I said to do this, but you put your tongue across there, the little 9 volts will go right through the tip of your tongue. And it's something to do on a rainy Saturday afternoon. What happens when the chemistry is done? You got a dead battery. All right, so the cell voltage is a function of the chemistry of the cell. That's what I want you to appreciate. And here's just some examples of different cells. You got your alkaline, you got your lithiums, you got your lead acid for automotive batteries, nickel cadmium. Those were and they still are used, but they're being replaced by nickel metal hydrides for safety. And mercury, they are being banned or phased out. Can you imagine the accumulation of very toxic mercury in all the landfills. Anywho, what's rechargeable mean? It means you can force that chemical reaction backwards. From the electrons in the cathode, force them back to the reaction in the anode. And then this is non-spontaneous. So you got to like plug in your rechargeable battery into an outlet. And then when you take it out again, it proceeds in the spontaneous direction. Okay. Alrighty. Look how much comes from lithium ion. That's a very high voltage. And lithium is very unique. And it is pretty much the state of the art in batteries. It was 25 years ago, and it is today. Here are just some batteries that, for example, I'm not going to ask you about these. I just thought you'd like to see some of them. The lead-acid battery, she's a 150-year-old technology in your little car, and she works just fine, thank you. And it's kind of funny because they both produce lead sulfate, which is a solid, so it's necessary to get that stuff knocked off of the plates. So if you make your guys sit around for too long, it won't reach, you won't be able to, it will hurt the battery and you have trouble getting it to work for you. The big advantage of this battery is it can be recharged by applying an external voltage from the vehicle's alternator, which itself is energized by the engine. Here she is. Lovely. Lithium ions, like I say, this is a very important battery because they're very light. They put out a lot of voltage, and they can be recharged hundreds and hundreds of times. And they give more watt hours per space and weight than any other type of battery. And if you see, more of 1 billion of them were sold in 2012. And this is how we have our portable devices, our mobile devices. But they're not without problems. They tried at the point I'm making this video, they are still trying to work out this problem. The Boeing 787 Dreamliner was the first passenger plane made with plastic composites, efficient engine, a lot of lithium batteries in series, and it had problems with fires. It's been grounded. They've tried many different systems, and the reason why they did this is because they get 30% better gas mileage on this. So you can imagine how wonderful that would be financially and for the environment. Okay, well, the problem is the batteries. Batteries hold back a generation. She's got a lot of cost, storage capacity, safety. They need a better battery. And that's why we don't have electric cars clogging the roadways. Too much money. The 787 Dreamliner sits idle. Solar energy, wind energy cannot be sufficiently stored when the sun or the wind goes down. Battery research needs to be the next big thing. They're talking about putting the kind of resources as the mini Manhattan Project. But appreciate this. No major advances in batteries have happened in 25 years. And in 200 years, we have had maybe 5 different successful rechargeable batteries. You know, remember the one from your car, the lead battery has been around for 150 years. So it's a big deal, and it's going to be very hard, and research labs around the world are working on it. Hybrids, you are familiar with their old hack. Now, full battery. The deal about hybrids is they can run on gasoline or electricity. You probably know that. They've got a 42-volt battery pack, and again, that's all these little lovely batteries in series, and stored in these permanent packs that they put into the car. They increase primarily the city mileage because that's where you run on the electricity. And the electronics are very sophisticated. They recharge. I like this one. They use the energy that would have been wasted in the brakes to regenerate. So here's some myths. You need a plug to put in a hybrid car. My brother still believed that for a long time. No, the plug-ins came in about 2011 that weren't just in small batches. The price is coming down on those. Hybrid batteries need to be replaced, not for a very long time. They are not small and underpowered anymore. The first responders have become much more adept at handling to approach hybrids in their very high voltage. And hybrids will solve all of our problems. Well, of course not. But they have been very useful in increasing the miles per gallon of many, many vehicles. And being at OSU, you have so many wonderful things going on. We have the CAR, which is the Center for Automotive Research. If you ever want to take a look online or take a look up there, they use the take advantage of the closeness of Honda, and they have done a lot of research on many different types of engines and fuel cells, energy storage, all sorts of things. Electric cars are feasible because 80% of us just travel less than 40 miles a day. They are very expensive, the batteries, but now they are dropping down. And well, you wonder how green they are. Well, electricity comes primarily from coal plants, and disposal or recycling the battery is unresolved. And so they are not totally green, but you have to look at the efficiency of the energy conversion. Another fun thing from OSU, the Buckeye Bullet. This is a totally electricity powered vehicle, and she is winning records as the fastest, 320 miles per hour as of 2010.